All right, so here we are going into Module 10, air currents. And this is a very big section, and it has a lot of stuff that drives weather. So let's talk about air first. Fun facts: it's mostly clear, it moves, and we need it. Those are things you need to know. Things that control air movement, and the following pages will talk about these individually. The density of your air, the amount of water vapor in your air, this thing called adiabatic heating and cooling, and this thing called latent heat release. So let's talk first about the density part of it. Density. Less dense air will rise and more dense air will sink. You're like, oh, well, that kind of makes sense. And what goes into density? The temperature and the water. So warm air will hold more water, and cool air will hold less water. And there comes a point, it's called the saturation point. It's the maximum amount of water that air can hold at a given temperature. And so these two factors, the density and the water vapor, play a big role in the next thing, and that is adiabatic heating and cooling. Oh boy. So check it out. You got some air down here, down towards the surface of the earth. It's 30 degrees Celsius, nice and warm. Because it's nice and warm, it can collect a bunch of water vapor. But as that air rises, it's going to cool off. As it cools off, it will also expand. This is because of those temperature pressure laws you learned about in chemistry. So, adiabatic cooling is the cooling effect of reduced pressure on the air as it rises and expands. So if you think about that, it's going to go up, it's going to spread out because there's less air pressure above it. And because it's spreading out, it will cool. All the same, sometimes your air will be brought down, it will compress and get warmer. Now this is really going to affect your water, because as you are warm and hold a bunch of water, as you rise, you can't hold as much water. Therefore, if there's maybe some rain coming, water's got to fall out of the sky. Adiabatic heating is the effect of reduced pressure on the air, and it shrinks. So there's less pressure, so it falls down. They work off of each other. So when we talk about latent heat release, we're talking about thunderstorms here. This time of year, perfect time to discuss this. Latent heat release is the release of energy when water vapor in the atmosphere condenses into a liquid. So all of a sudden, it goes from water vapor into a liquid, and boom, energy is lost. Because of the latent heat release, the air that lost the liquid water gets warmer and it rises. So down here, it's denser and heavier. Okay? When the water's fallen out of it, it gets pushed up. That's why in the summer, in the beginning of your thunderstorm, you just see them building and building and building because they're starting to lose that water and the energy is pushing them up. Then you get your mature thunderstorm. You'll notice in the front of it, it's welling up. You can see the clouds. I love watching it. They just build and billow and make all these cool shapes. But then, because of that energy loss, there's energy loss, the water falls out, we get the thunderstorm. Once the thunderstorm's done raining out, you get this kind of worn out cloud up here. It's already given away energy. It's given away the water. And part of this has to do with convection currents. And there's small-scale convection currents, but there's also very large-scale convection currents. We will talk, let's see, scroll down. When we get into this stuff in another section, we'll talk about convection currents that drive our ocean's motion, okay? I don't know if you could see that. I have it on the tab. You can probably see that. But it really drives oceans. But equatorial heating causes air to rise at the equator. So you're at the ground, the sun's blaring on this thing, it gets hot, it rises, but as it rises, it expands and cools. And then once it gets cool, it pushes down, and you get yourself a cycle. This has a lot to do with the entire global air pattern now. I have a video. If you want to Google this, put convection current tank, and you'll see examples of this thing here. I have a video. I don't think I can click off it during the recording. to see how the convection, how the blue will push over and the red will push over, and you make this nice little circle. Okay. These convection currents power the convection cells. I have this image bigger on the next slide. So there's a cell called the Hadley cell. And the Hadley cell is your equatorial cell. It goes from 0 to 30. And what happens is you get all this heat along the equator. That heat drives the air up. Now, behind it, that drags other air along to get heated up and push. Once it gets heated up and pushed up above, it cools and gets pushed back down, or settles back down, just to be redistributed back to the equator. And so this is your Hadley cell. Now, mirror images north and south of the equator. Okay, we like to focus on the north hemisphere. So you get this Hadley cell. It rotates like this. Well, there's also a polar cell that does the same kind of deal, but in reverse. It's cold and it pushes other cold air down, and you get this polar circulation. When this polar circulation just kind of takes a visit down south, that's when we get our polar vortex, and it's so cold that the air hurts our nose. That's our polar vortex. If you look at the picture, you can kind of see the Great Lakes here, and you can kind of see the polar front is kind of bumping along there. This can dip down to us, but it's a feedback cycle, cold and cold and cold. The Ferro cell is powered by the two of them. The air pushes both ways here, pushes both ways, but then it bumps up and it just circulates here. And this is the one that a lot of our weather is stuck in. Okay? Now, this also ties in with something on, go to this page. So here's a closer picture here. So the air gets heated and pushed and circulated here, cooled and pushed and circulated here. Then this one's stuck in the middle, running off the other two. Imagine you're at the gas station and there's the hot dog rollers. Well, the one roller goes this way, the other roller goes that way, and the hot dog spins in the middle. If you just need a visualization. And that ties in with the Coriolis effect. Perhaps you've heard of this. The Coriolis effect is the deflection of an object's path due to the rotation of the Earth. Imagine you're at the North Pole and you want to throw a baseball to your friend at the equator. So you throw it. You think you're throwing here to them in the ocean. The reality is, as you throw the ball, the Earth spins from underneath it and it curves to the side. This curving to the side is the Coriolis effect. And that causes our entire air masses to spin along the surface of the Earth. This does not affect you driving in a car. It's not going to affect you shooting a bullet out of a rifle. It would affect you flying an airplane. It would affect weather systems. So check it out. If you look at typical hurricane paths, our hurricanes are born off the coast of Africa. Dust and wind blows off of Africa, and it helps seed the thunderstorms with the heat along the equator. They come here, and you start to see them take shape, and boom, here you go. You got hurricanes. Some hurricanes also form off into the Pacific. They call them cyclones over there, but or typhoons, cyclones, whatever. They're all big weather systems. But the Coriolis effect causes them to do this churn, and you'll notice the typhoons do the same thing, and the cyclones do the same thing in the south. Okay? The Coriolis effect causes our hurricanes to spin counterclockwise, and over here they spin clockwise. They do not cause toilets to spin different ways. By the way, the Coriolis effect has nothing to do with that. If your toilet spins the other way in another country, it's because the design of the toilet. Okay? This is how we get this beautiful spin on our storms. Okay? I wonder what what weather system that was I captured. So you get global wind patterns. Now, global wind patterns are driven by the cells. So you got your polar cell spinning this way, you got your Hadley cell spinning this way, and of course the weather cells that affect us. You'll notice that a lot of our weather comes up, California way and across. This is just the general prevailing way of our weather. It doesn't mean you can't go kind of opposite sometimes. This is the general idea. This also drove, in case you weren't aware, this drove the African slave trade. They would come off of Africa, and because of the weather, they come off Africa and they'd hit up here in the Caribbean. They'd trade slaves for rum and sugar, and then come up here and they'd have slaves and rum and sugar, and they'd come back to England with rum and sugar and slaves. And it was this great big spin. Okay, powered by our global weather patterns. When you're talking about global weather patterns, you also need to talk about this thing called a rain shadow. And this is a big deal out west. It doesn't affect us here in the east nearly as much, but I can point to a place on the eastern side that there's a little bit of effect. But out west, you get this tall mountain. And your moist air off the ocean comes up the mountain, and as it gets pushed up the mountain, it cools and it rains. And so this side of that mountain is beautiful and green, and this side of the mountain is a desert because there's no more water left. Let's examine Hawaii. The prevailing wind is from the northeast. So the northeast wind comes, the rain comes up the volcanic mountain, it rains out, and then there's just not that much rain left for the southwest side of the island. So the trade winds, they come, and look, you can see more green over here, less green over here. That's what happens. It's a rain shadow. The place it affects us, just east of some of the tallest parts of the Appalachian Mountains. There's a part of West Virginia, like that panhandle of West Virginia that goes over towards Virginia. It's very dry there, comparatively. Because a lot of times, the weather coming up the Ohio River Valley, it really rains itself out on our side of the Appalachian Mountains. And there's just not nearly as much water left just past the mountains. Then the eastern seaboard gets its own weather and gets its own rain. And this is the end of the section.